In this lesson, we're going to take a look at how we can utilize the metal ray dielectric material. So the dielectric material is a material type within metal ray that has the ability to physically simulate in a very accurate way the way that things like refractive and reflective objects will behave in real life. So this dielectric material utilizes something called a Fresnel effect, where the objects or the areas of the object that are more directly facing toward the camera are less reflective or refractive, whereas these areas that are facing very heavily away from the camera, you can see they contain a much higher level of refractivity. So this is what the dielectric material will allow us to simulate. So let's take a look at how we can start to implement this. So we can first start by dropping in the dielectric material. And in our case, we actually have two different pieces of geometry in this scene. And we'll see why here in just a moment. But for now, let's get started by just selecting these two pieces, assign the dielectric material, and just quickly hit render. Now, if you first render in a brand new scene, you'll probably notice that the dielectric material actually comes out pretty much black. We have no transparency whatsoever. So whenever using the dielectric material, since it does make use of ray tracing, reflections, and refractions, we want to make sure that the number of rays is set up to an appropriately high level. So in our case, let's try something like 5, 5, and 10. There we go. And now you can start to see automatically we get the refractive ability, and we also have the Fresnel effect that's already built in for us. So let's take a look at some of the attributes that are going to control this dielectric material. The first is the color. This is basically referring to the color of the ray as it enters this material. So in our case, if we wanted this to be more of a green glass, we have the ability to very easily control that. So just below that, we have the index of refraction, which more or less controls how far the light is able to refract as it passes through. So with an index of refraction of 1, we should see no refraction capabilities whatsoever, which is exactly what we see. So typically, most liquids will have an index of refraction of around 1.3, whereas most types of glass will have an index of refraction of around 1.5. Although the exact index of refraction may vary depending on the actual material that you're trying to simulate. Now, the outside color and the outside index of refraction come into play whenever we try to create some kind of a dielectric to dielectric material interaction. What we have right now with the color and the outside, or rather just the index of refraction, will be perfectly fine if we're trying to simulate some kind of an empty vessel, like an empty glass. However, if we wanted this glass to be able to be filled with some kind of a liquid, that liquid would most likely be dielectric as well. That's where we start to get into dielectric to dielectric material interactions. How does this dielectric glass interact with the dielectric material inside? So we can start to see that if we were to start to add in a new dielectric material. Whenever we start to create dielectric material interactions, it requires actually several different pieces of geometry to actually encompass the entire effect. So right now, this dielectric material will be set up for the glass. And we'll go ahead and name this accordingly. So index of refraction of 1.5, and this will give the glass a white color as the ray enters and as the ray exits. This is basically what the outside color is referring to. We want to leave the outside index of refraction set to 1 for this glass. So that way whenever the ray reaches through this first layer of the glass and then reaches this area right in here, this open empty space, we want it to have an index of refraction of 1, which is basically air. Alright, so let's come back to the metal ray nodes. Let's add a new dielectric material for our liquid. So in this case, we'll call this liquid material. Now if we wanted this liquid to be more of a blue color, we'll have the ray as it enters the liquid be blue, and then we'll have the ray as it exits the liquid be blue also. Now this is where these values become very, very important. The index of refraction as it passes into this liquid, we would probably want to be around 1.3, since that will be the refractive index of most types of liquids, and then the refractive as it passes outside, we want to be about 1.5. So what this means is if this piece of geometry, which is actually just the hollowed out portion of this inner piece of the glass, so we want the ray, whenever it passes in, to have a refraction of about 1.3, so that way we see most of this liquid as it is, and then as the ray passes back out, we want it to be 1.5, so that way it has the appearance of being up against this glass, which also has a refractive index of 1.5. Alright, so let's go back to our view. There we go, and now we can start to see the dielectric effect of this liquid that's inside. Now for our final piece, we need to actually have a separate piece of geometry that will act as the cap for this liquid. So you can see this is really just the top. And for this, we'll add yet another dielectric material. So we'll middle click, drag and drop this on here. Now for this one, we'll go ahead and leave the color in and the color out both set to white, since this should inherit its color from the dielectric material that's inside that we just set to blue. And for this one, we'll set the index of refraction at about 1.3 to match the liquid. So that way, when the ray is passing into this surface, it should have an index of refraction of 1.3. But since this particular object does not have any glass on either side of it, whenever the ray exits, we want to have it have a refraction index of 1. So that way it matches the index of refraction that you would have if it were to just simply interact with air. And now you can start to see the effect of the liquid at the top of our glass. Right now you will start to notice that the materials overall are starting to darken a bit, so we probably need to go back and increase our number of rays again. And now you can see that that looks much better. Although, now if you look at our rendered result, you can start to see that there is an error that we have, and that is that we actually don't have any of this blue liquid color right in this area as we start to pass our refraction rays through the glass itself. However, you can see behind here that there is a very strong blue color, and below as well. So this is where we need to come in and actually go back to the dielectric material and most likely start to give it some kind of a blue color as the ray enters this liquid. And if we want to, we could probably actually go back to the glass liquid itself and start to take note of these RGB values that we have here. So you can see that the color is a little bit darker. So let's actually go back to the dielectric material, which is this material up at the top. So we'll open up the color chooser. And with this color chooser still open, we can just go back to the dielectric material, sample this color, press accept, and that way we can make sure that we actually use this exact color over in the material that's going to be at the top of the liquid. And I should probably go ahead and rename this. So let's save our rendered result for comparison. And there we go. Now you can see how the ray, whenever it enters this material, as far as the top of the liquid is concerned, will now have this blue color. Alright, so that's a look at how we can start to utilize these dielectric materials and how we can utilize multiple dielectric materials on multiple objects in order to get these dielectric material interaction effects. Now, one last thing that we need to take a look at before we finish up this lesson is the actual normals on our geometry. Now, this dielectric material is very particular about the normal direction that you use. So in our case, we have this inner piece of geometry, which is the blue liquid that's standing inside the glass. And you'll notice that the normals are pointing inward. Right, this becomes a little bit more apparent if I were to turn on the normal display for face normals. And in our case, these normals are a little bit too big, so let's take this back down a little bit. There we go. So for these liquid materials, we want to make sure that the normals are pointing outward, so that way we get the correct interaction of the surface that is meant to be pointing out. So let's go back to normals, and we'll reverse the normals on this geometry. These normals will leave pointing outward, and the normals for this piece of geometry we'll want to make sure they are pointing up, which they are. So now let's go back. Now that we have the normals for this inner portion that have been flipped around, let's compare our result. So here's what we had before. And now you can see how that gives us a result that is a bit more accurate compared to what we had before. You can really see the difference along this top portion, where now we can actually see the reflections and the refractions that we would get if this were a dielectric liquid that we're touching right up against a glass. So the normal direction and the materials that we assign to each object do make a very, very important difference. So that's a look at the dielectric material.